So hello, I will be presenting on ARQ protocols. So first, what is an ARQ? So ARQ is automatic repeat request. So it ensures the data is reliable to transmit even over an unreliable network by requesting retransmission when the data packets are lost or corrupted. So what is flow control? Flow control is actually one of the techniques in computer network. It regulates the data transfer between the computer and other nodes. So flow control is actually very important. Why? It ensures that the sender does not overwhelm the receiver by controlling the pace of the data transmission. So this is crucial in situation where there are speed mismatches between the sender and also the receiver. So we're back to the ARQ protocol. So there are three common protocols. So the first one is stop and wait ARQ. So this works by sending one frame at a time and wait for the ACK before sending the next one. So the next one we have is the go back and ARQ, which improves upon the stop and wait ARQ by using sliding window that allows the sender to transmit multiple frames before waiting the ACK. However, if any frame in the window is lost or corrupted, all the subsequent will be resent. Now let's look at selective repeat ARQ, the most efficient ARQ among these three. And why would I say that? So, the selective repeat ARQ also uses sliding window. But unlike the go back and ARQ, it only retransmits the lost or corrupted frames.
Hello everyone and Dr. Law Seping. My name is Felix and matrix number is 104174. So today my part will be presenting for experimental setup. Okay, so here we got total 4 test cases. Now let's talk about the first one, ideal network. Condition of ideal network is low package loss, high bandwidth, and low latency. Purpose of ideal network is to simulate near perfect network conditions, and the expected outcome are minimal retransmission, high throughput and bandwidth utilization, and all ARQ protocols should perform well, but stop and wait may underperform due to idle wait time. Okay, the second one is congested network. Condition of congested network is high package loss, low bandwidth. Purpose is to test how ARQ protocols handle severe congestion, and the expected outcome are increased retransmission, especially for stop and wait and go back and end. Second one is lower throughput and utilization. Next is selective repeat, expected to perform better by minimizing redundant retransmission. Okay, the third test case is high latency. Condition is long network delay with varying timeout intervals. Purpose of high latency is to evaluate protocol sensitivity to delays, and the expected outcome are stop and wait likely suffers due to frequent idle times. Timeout values need to be well tuned. Too short cause premature retransmission. Too long increased delay. Next, sliding window protocols like go back and end and selective repeat handle this better due to pipeline effect. And the last fourth test case is window size. Window size, its condition is compare small vs large size only for go back and selective repeat. The purpose of window size is to understand the effect of window size on throughput and retransmission. Expected outcome are larger window size improve throughput, more frames sent before needing SCKS. Go back end may suffer with largest window if one package is lost, many packets resent. And selective repeat benefits most from larger windows with fewer unnecessary retransmission. Okay, for this part, and we see the last test case, window 4. Okay, this simulation for test case 4 is repeated 3 times, each with a different window size 2, 4, and 8, while keeping everything else the same. Okay, now look at the next slide. Okay, test case overview. Okay, the first test case is to optimal network condition. Package loss equals to 0.01, bandwidth equals to 100% 100 Mbps, stimulate ideal condition with minimal loss at high speed. All protocol perform well, but go back end and selective repeat achieve higher throughput than stop and wait due to pipelining. The second test case is poor network quality. Package loss equals to 0.3 and bandwidth equals to 2 Mbps. Stimulate a congested, unreliable network. Stop and wait suffer high retransmission. Go back end best bandwidth due to full window retransmit. While selective repeat perform best by retransmitting only lost packets. Okay, the third test case, the value used is high latency equals to 200 ms and timeout is equals to 300 ms. Represent long distance or satellite network. Stop and wait become very inefficient due to high waiting time. Go back end and selective repeat perform better by keeping the pipeline full. And the last test case 4, value used is window size equals to 2, 4 and n, and to test how window size affect throughput. Largest window improve performance for go back and n. And no effect on stop and wait. Always window size equals to 1. Okay, now look at the next slide. Simulation result table. For each protocol under each test case, we have recorded the output for total package sent, total package retransmit, total SCK receive, and total SCK loss and total transmission time. Okay, so on the right side we can see, so that is the result of the table. Okay, so we can make the final conclusion with the table is stop and wait is simple but inefficient, while go back and end is better than stop and wait but suffer from unnecessary retransmission. And last, selective repeat is the most efficient and reliable, especially at higher window size with minimal retransmission and transmission time. Okay, I think that's all from me. Thank you.
Let's begin by looking at transmission time. Okay, this chart shows how long each ARQ protocol took to send test packet in different conditions. You can clearly see that stop and wait take the most time, especially when delay or loss are involved. Go back end improved as the window size increased but still rather in poor condition. Selective repeat performed the best with lower transmission times across all test cases. So this helps us use the network more efficiently. Okay, now let's talk about the retransmission. This chart shows how often each protocol has to resend package. Stop and wait and go back end both show more transmission, especially when there is packet loss. The selective repeat has fewer retransmission because it's only resend the lost package, not the whole sequence. So fewer retransmission usually means better use of bandwidth and less delay. And now, next slide. Next, we compare the total number of packets sent. Here, stop and wait send the most packets, which indicates higher overhead and lower efficiency. As we increase the window size for go back end and selective repeat, the total packet sent became lower and more stable. This is because this protocol can send multiple packets in one go, reducing repetition and saving time. So now I will present about the analysis and discussion. So for our simulation, we look into 4 key factors that affect ARQ performance: packet loss, bandwidth, latency, and timeout. When packet loss increase, stop and wait is hit the headers, causing index time and delay. Selective repeat headers is better by only resending where they are needed. For bandwidth, stop and wait rest and loss because it wait after each package. But go back end and selective repeat keep the line busy with more backup in the pipe. Latency also play a big role. Stop and wait so well as delay as rise. But in the protocol like go back end and selective repeat help mask that delay. Lastly, timeout setting method. So short timeout lead to accelerated distribution. Long timeout delay recovery. Selective repeat again stand up. Its balance list will by targeting specific package. So in the conclusion, selective repeat ARQ get the best performance under almost all conditions. It's fast, efficient, and handle loss and delay well. Stop and wait was the simplest to use but struggle with performance, especially when network were perfect. Back end was better than stop and wait, improved when we increase the window size. In short, if you are working with network that is experiencing loss or delay, selective repeat is the smart choice. So I think that is all for me. Thank you.
Now we are entering the part B for the project is communication and computer network, which is the implementation of network design proposal for Naomi Sandrian Berhat. The objective are as follows, which is to apply theoretical knowledge from the communication and computer network courses into a real-world network implementation scenario, design a practical and cost-effective computer network for the company Normies and Berhat that meets both general and specific business needs, and also to ensure efficient internet sharing, smooth support for wired and wireless connectivity, shared printing, and secure guest Wi-Fi access across the 2 office levels. The requirements are as follows. For Office A, there are 15 stationary employees and 5 mobile employees, and for Office B, there are 10 stationary employees and 3 mobile employees. For stationary, we simulate it as using PC. For the mobile, we using laptop or smartphone as the representation. As for the printer, the Office A required 2 network printers, whereas the Office B required only 1. As for the guest Wi-Fi, it is required restricted Wi-Fi access in both offices, meeting rooms for the guests. Now, as you can see on the diagram below is our network design overview, whereas on your left side is the topology for Office A, and on the right side is the topology for Office B. We begin by creating the internet gateway by using the single ISP or cloud connection with the 500 megabyte per second downlink and 300 megabyte per second uplink, and it is shared between both offices, and it's connected to the router, and which helps managing VLAN routing, JCP, and internet access throughout the whole offices, and is connected to the switch. For switches, there are 2 types of switches we're using, which are the core switches and access switches. The cores help handle the VLAN trunking between the offices. As for the access switch, it helps to support PCs and printers. The wireless access points are directly connected to the core switch for the employees, Wi-Fi, and the guests. We implement VLAN segmentation and inter-VLAN routing between offices for efficient communication. So, for instance, like for employees in the Office A, the PC is set to VLAN 10, whereas the printer is set to VLAN 30. As for the guest Wi-Fi, set the VLAN to VLAN 40. By using different VLANs, we can allow that the guest can only use for the guest Wi-Fi only. Up next is the network requirements for Office B. Almost the same as the Office A, just the difference is the number of end users around the access switches, as well as for the core switches. So the same function is to help handle VLAN trunking between the offices. So as for Office B, we set using the VLAN, we set VLAN 20 for employee in Office B, and wireless access point are also directly connected to the core switch for mobile employee Wi-Fi. And for both offices, they are using wired and wireless connection. And this is our cost-effective diagram implementation for Narmi Syndrome Berhat. But if I do want to add some modification, I maybe for one like wanting to add the connection between the router to the core switch Office B for future prevention, in case that if one of the switches suddenly malfunction, we have another connection for the router to another switch to directly share the internet through the all users to end devices, and as well want to connecting the core switch B to the guest Wi-Fi as well.
Wire versus wireless setup justification. Wire connection, Ethernet. Reliability and performance. Wired connections provide stable, high-speed data transfer with minimal latency, making them ideal for servers, workstation, and critical infrastructure. Security. Less susceptible to interference and eavesdropping compared to wireless. Bandwidth-intensive applications. Best for high throughput needs, example, video editing, large file transfers. Wireless connection or Wi-Fi. Mobility and flexibility. Allow seamless connectivity for mobile devices, laptop, smartphones, IoT. Reduced cable clutter. Simplifies deployment in open spaces and reduces infrastructure costs. Scalability. Easy to expand coverage with additional access points, APs, without rewiring. Hybrid approach. Combining wired and wireless ensures optimal performance where needed while providing flexibility for mobile users. VLAN and access point justification. VLANs or virtual local area networks. Enhanced security. Segments transfer traffic to isolate sensitive departments, example finance, HR, from general users. Improved performance. Reduces the broadcast traffic, optimizing network efficiency. Simplified management. Allows logical grouping of devices, example IoT or guest networks, without physical rewiring. Compliance and access control. Enforces policies, example, restricting guest access to internal resources. Access points, APs. Coverage and roaming. Strategically placed APs ensure seamless connectivity across the facility. Load balancing. Distributes wireless traffic to prevent congestion. Dual band support. 2.4 GHz and 5 GHz. Balances range and speed for different devices. Centralized management. Modern APs. Example, using a controller. Allow easy scaling and monitoring. Practicality and scalability of the design. Practicality. Cost effective. Uses existing cabling where possible, supplementing with wireless for flexibility. Future-proof. VLANs allow easy reconfiguration without hardware changes. User-friendly. Wireless access reduces dependency on physical ports for mobile users. Scalability. Modular expansion. Additional APs can be deployed as user density grows. VLAN flexibility. New departments or devices can be added without restructuring the physical network. Cloud managed solutions. Allows remote adjustment and monitoring as the network expands.